Okay. Hi everybody. I'm Fan Xie. I'm going to present this paper named Better Time Constraint Search with Randomization and Postprocessing. This is a joint work with Richard Valenzano and my doctoral supervisor Martin Mueller. And before we start, I'm talking about some background first. Yeah. Basically, I'm focusing on satisfied planning. So for last IPC competition, most satisfied planning planners basically try to iteratively improve their plan quality through some anytime approach. Basically, we want to find a solution, the first solution very quickly, later try to improve it by use current best solution as a bound to pruning the search space. However, if we use the current anytime search planner with a post-processing plan improvement system such as ARAS, the bounding strategy which you use to help pruning the search space might be very helpful. Basically, the very simple reason is a low quality plan, if you use post-processing system to improve it, it might result to be very high quality plan. So I want to show some basic intuition why that happened. So we have the post-processing system which named ARAN. It's basically this system take one solution and build a neighborhood search subgraph of this plan and run a shortest path algorithm in this subgraph. Here, assume that we have the solid black line as the input plan. Then we have a neighborhood search space which is defined by the dashed black line. Later, after we run some shortest path algorithm inside this search space, we get the red line and shortest as the new plan. Then we look at the second picture here. Here we have quite longer input path, but because it's a longer and the search space, sometimes we can get some shortcut here, which make you get some better quality plan. Now, before we're talking about my approach, I want to show some statistics about why I think about to introduce my idea. So here, I want to define something called unproductive time first. What is unproductive time? This is the amount of time remaining out of the total time given. That's why the planner best solution is found. Actually, basically, one example is, for example, we have a plan. We have a planner find one plan which is like 30 minutes, giving a 30 minutes time limit. If the planner cannot improve this plan quality in the following 70 minutes, we call this 70 minutes is unproductive time. Basically, you are doing something probably, but you are not improving the plan. So then we go to Llama 2011. We want to check how about the unproductive time for this planner. So here we have the y-axis is the interval of unproductive time, and the x-axis is the number of programs. Llama 2011, in IPC 2011, we saw like around 240 programs, and actually nearly half of the program, you just finish finding solution in the first 100 seconds. All the remaining time, keep searching, but no result. I got something like, okay, we have so many time left, but we're doing nothing here actually. For the unproductive time, there's some difference for varies on different domains. And I list the domain according to the percentage of unproductive time. Here we can see for printer, we have like percentage of 99.99%. And nearly only this domain, Llama just simply find the solution very quickly and stay there. Nothing happened anymore. And then for some other domain like parking, we have like only 43% of unproductive time. So Llama actually still improving the plan during the search time. And since now I'm asking something like why? What's happened there? Why have we have so much unproductive time? For llama, this bundle itself, there are two reasons. The first one is the first iteration, llama used grid-based search with some distance-based heuristic, FF heuristic, or distance-based landmark heuristic. This makes search easier to find some solution. Once found the first solution, it's moved to some harder configuration. And also, the hard configuration is easier to find better quality solution. Another thing is bounding. Because we use the count-based solution to prove in search space, many easy solutions might not be found. Also, look at about how llama works on IPC. We think about some post-processing system we call ARAS. I have introduced this picture before, just a couple of slides ago. This is the basic idea of ARAS, how it works. It's a post-processing system and build a subgraph along the input plan and run a shortcut algorithm in the subgraph. So we mentioned that it's possible that a low quality income solution might result in some high quality outcome solution if it goes through ARAS. So what's it happen? What's the reality in IPC and llama? So we run ARAS with like 2 GB memory and on all plans that llama generated for IPC 2011 domains. And then we found a surprisingly 29% for program, the lowest cost solution is generated by an earlier plan, which is not the final plan llama gets. Which means some plan just maybe not as good as the final plan, but after ARAS, it may be better. So there one typical example, which is transport 07. Llama 2011 generates 2 plans. One which is, the first one is cost like 8,000 cost. And the second one is 7,000. But after processing, the first solution goes to like 6,379. The second one, which is stronger one, which results like 6,400. Yeah, that's the case. We have many cases here, 29%. So now we get some idea about llama. Okay, it gets a lot of time not really used, which is unproductive. Also, we get some ARAS can be improved, some low quality plan, even to better quality plan. So what we can do? Firstly, one simple idea, we can run ARAS on both the best and non-best solution. This is one solution, one idea. Another idea is when it's very hard to find some high quality solution by llama, can we just increase the chance of finding low quality solution? And hopefully, the post-process system will help us find a higher quality solution. So for example, we can restart the search without bounding, something like that. So let's go to these two ideas one by one. The first one, we are thinking or look at how ARAS and bounding works with llama. So here, there are two configurations I propose for using ARAS with llama. So the first one, we can run llama. The first configuration gets plan, and use ARAS to improve the plan, gets another plan PA1, and then use P1 to bound P2. Here, I'm not using the ARAS plan to add bounding and to bound the following search. This is important. And the second configuration, I use the improved plan by ARAS to bound the search. Actually, this is more tight bound actually because improved by the local graph already. So let's look about the result. So here we have llama 2011 original llama. We have llama ARAS, which basically is the one we are not using the ARAS quality plan to bound the search. The third one is llama ARAS with bounding, which basically you always bound with the best solution. So look at this. Let's forget about all the number here first. Now look at this line. It seems this one actually not using bounding with ARAS plan is working well, working better. And also you can look at this. The formula Actually, the bolder number are just the best solution, best score in this domain. Basically, you can see that this planner just dominates all the domain, except one, which is OpenStack. This reason is the search space of OpenStack just is a tree. So post-processing not working in this domain. It's just search space is a tree. So now, after we have looked at about the post-processing, how it improves plan quality, let's look about the restarting actually. Here, assume we have the 30% time cutoff. Yeah. If you want to really generate more plans, one very simple idea is we do restart. So what I did here is I just make this 30 minutes to n equal time segment, and inside each time segment I run llama. And one very important thing is when you go to the second time segment, I just totally forgot all the knowledge I have from the first segment. Because then I can just start no bounding, no nothing at all. I just run another llama, but with some randomization. So here let's look at the results actually. Here again, I sort the domain based on the percentage of unproductive time, and then you can see that in some domain, this is llama. This is diverse llama, which basically I will do several restarts. Here, the number is 4 means I do 4 restarts actually. And we can see that in some domain it's improved, in some domain it's not improved, it's actually getting worse. That's why this is the basic reason. If for some domain that's with high unproductive time percentage ratio, basically restarting not harmful at all. Because basically your llama just not doing anything after some time range. So you just do some restarts in this kind of time range, not harmful anymore. So basically still improve a bit, but actually not very significant. And we look at this picture paper will be more meaningful for you guys. So we can see that here we show the number of problems this restarting policy really improves, and the number of problems is become worse, and this is total number of problems solved. We can see that according to the, again, I ordered this domain based on the ratio of unproductive time. We can see that when the ratio of unproductive time is high, basically this idea works. It's already improved, and there are no worse solutions. And once you go to the time, the domain that we have a lower unproductive time ratio, you see that sometimes it's very often to get some worse results. Yeah. Now we have two parts. One part is ARAS, which is a post-processing system. Another part with some randomization. And we have some restarting policy that can generate more low quality plans. Now we try to combine them. And then before I really talk about combining them, I do some trade-off here. So really, the high quality input plan is very hard to find actually. But generally, you will get some higher quality to get a better solution from after ARAS. And the low quality plan, which is easy to find, but the probability to get high current output plan is low. So this trade-off. We always want to find high quality plans. But when it becomes very expensive to do that, we will try to change our strategy to find some more low quality plan. Here is my algorithm, which is basically the combination of these two. Firstly, we divided the time cutoff to certain range, and in each range we will run llama, but with this time with ARAS. Here is basically the result of based on the parameter n, which is the number of time segments you have. It's some trade-off, like when it becomes 1, and basically it's llama with ARAS. But when here you get some value improvements when it's equal like 4, 5, 6. Later you decrease, mainly because you don't have enough time to get good quality input plans. So let's look at a bit more results. Here, we are testing on IPC 2008 and IPC 2011. We have Llama, which DL4 basically is restarting policy Llama. And here is Llama ARAS, and here is restarting Llama with ARAS. And we basically can see that it's improved, which is get the best score here. And actually this score is higher than the improvement of these two planners, the sum of these two planners. This picture is a bit more interesting here. Here we have the normalized score here, the y-axis, x-axis is the time. And these three vertical line, which is actually the time we do restart. Because it's logarithm scale here, so it's not equal. Yeah. So we can see that the green line is Llama, the red dashed line is actually the restarting Llama. Here we have Llama with ARAS, and the Llama diverse, and the restarting Llama with ARAS. We can see that after each restart, actually the quality, we can see the gap between this planner become bigger. Okay, we also wondering in the beginning whether that's because Llama not generating a lot of land later. So we try to also test our algorithm on some algorithm that's designed to generate more plans. But actually, we tried many algorithms, but actually here, we only found that AES, which is from Jordan and Euler, which can solve considerable problem that we can really compare to. And also, they have some nicely bound, suboptimal bound, that we would like to see. Okay, we also see that in this domain, in this algorithm also gets some very interesting improvement here with similar results. Now, let's do a bit summary of my work. So firstly, we'll introduce the concept of unproductive time, which will help you understand the time usage of different planners and also the impact of bounding. We also present some evidence that as always bounding might be in an anytime search might be not very good, might be harmful when you have some post-processing system. And then we also propose a meta-algorithm which is diverse anytime search, which you can combine any anytime search planner and the post-processor to improve plan quality. Here, just a basic, a small difference for you guys. Maybe for you people who really familiar with fast downward, you can see that this basically is Llama, the configuration for Llama. But the only thing I change is, I guess, like iterative ARAS with. I replaced the iterative search by this kind of search. Actually, we implemented ARAS. We implemented my algorithm in the newest fast downward code base. So no matter which, you only need to modify one line to get from your plan quality, your IPC score from 500 to 570. That's some interesting thing, and it's a general framework, and it can be applied for any kind of planners. Okay? Basically, this is my presentation. Thanks.
Thank you.